Now we'll discuss about how we can make a multi-bit full adder circuit, right? One bit is just okay, one interesting point, but what we at the end of the day, we need a multi-bit full adder, right? Either 8-bit or 16-bit or 32-bit. We'll start with like 4-bit full adder, and we'll discuss only one specific type of addition circuit, which is called binary ripple carry adder. There are multiple variants of addition circuit, uh, but for our purpose one discussion is sufficient just to make sure we understand the underlying digital concept. Okay, and we'll do for the 4-bit. This 4-bit ripple carry adder study is sufficient because you can make multi-bit like 5, 6, 8, 64, 255, any number of bit ripple carry adder in the similar fashion, where we deploy like full a 1-bit full adder in a daisy chain connection. Okay, what does it mean? If you look at like this CO and CI is the input for the full bit adder circuit, 1-bit full adder circuit, and CO is the output of that. So first stage output, or LSB side if you want to call it like that way, LSB sides carry out connected to the next higher bits carry in, and then that adder connected through the CO to the next higher bit full adder circuit to the CI carry in port, and so on and so forth. So we can extend the same circuit like adding more and more full bit adder into it, make a more than 4-bit ripple carry adder. And each stage, A and B, that bit, we keep on connecting the LSB from the LSB to MSB side of the two operands, right? We have two values, let's say register A and register B is holding those 4-bit in this example, and they call it A3, A2, A1, A0, and B3, B2, B1, B0. The individual bit name are these. So we connect A0 and B0 to the LSB side full adder. Then comes A1 and B1 connected to the next full adder, and then A2, B2, and A3, B3. So at each stage we are computing corresponding sum, right? So LSB side full adder gives you the sum S0, and next one gives you S1, next one gives you S2, next one gives you S3, sums 3, and that 4-bit together become your sum bit. And of course another important is your last or MSB side full adders carry out, which basically your overflow indication, and that goes into an overflow register, so that when software uses like A plus B, like 32-bit, let's say we have 32-bit ripple carry adder, then software can also check this overflow register to see if the addition result was like, is it a complete addition result that could fit into 32-bit or not, right? In this case, is it going to be fit into 4-bit or not? That is indicated by your overflow register. If the overflow register content is 0, then I can safely take from the register C all the sum bits as my sum result. If the overflow bit is 1, then register C, whatever bit pattern is there, is not the right sum result summing between A and B. So this is your logic circuit of a 4-bit ripple carry adder. So now you can well imagine it has like 4 full adder. Each of the full adder has 2 half adder and 1 OR logic gate, and each of these half adder has one and another XOR gate in it, and then one XOR contains basically inversion and or those kind of logic like A bar B or A B bar, and each of these logic gate contains your transistors as a basic building element, electronic element, to build up this whole logical circuit in as an electronic circuit. right? So you can well imagine, even for the 4-bit ripple carry adder, how many transistors are actually involved there, how many devices, little devices are involved there. So please make sure you understand those abstraction, right? Our physical device is transistors, and as we go up, multiple transistor together becomes a logic gate, multiple logic gate together becomes like 2 half adder in this case, then 2 half adder and another OR gate becomes a full adder, and 1 bit full adder, then we connect 4 full adders in a daisy chain way to make a 4-bit ripple carry, binary ripple carry adder. Why the name binary ripple carry? You can imagine your carry is kind of rippling through these components, right? Your first stage is creating one carry, which is triggering generation of another carry in the next stage, which is triggering another carry for the next stage, and so on and so forth, right? So this is kind of your carry is rippling out through the next successive stages, and as it goes on completion from stage 0 to stage 1 to stage 2 to stage 3, your sum bits are also in sequence. They are being computed and deposited as a summation final result. So that's your ripple carry, binary ripple carry adder.